So today we are going to discuss something about the application of custom power devices and its application in wind-based DG system. Means in this case we are going to discuss something about the design and control of some filter or maybe switch filter. After that, their application in wind-based distributed energy system. Maybe you can say zero energy system. Both are same thing in case of wind. Okay. So first we are going to discuss something about the custom power devices. Inside of this one, maybe you can say these are the inside of this one we have two types of devices. First one the maybe configuration type. Second one the compensation type. In case of configuration type, those work as a just like a breaker only. Just they are going to provide the path. But in case of compensating type of power devices, they are going to provide the compensation. Then dynamically they are going to provide the compensation for voltage, current, and both. That depend upon the types of power device, whatever device we have used. In those cases. Okay. Then after that, you can say what is this? After that, we will discuss means different custom power devices used for the compensation purpose only. So first one is distribution static compensator. Second maybe you can say DVR. Third maybe we can say unified power quality conditioner. Now we will discuss only some basic operation, how they are going to operate, design, some control I will discuss about this one, what are the operating mode. After that we will discuss application of the sun filter, this state coming wind-based system. Okay, so in this case we will not discuss so much detail, just whatever thing means we need, that one I will tell only. So now you can see what is the application of custom power device, custom power device. This is mainly used for the compensation of reactive power. Additional features are harmonic compensation, load balancing, and neutral current compensation in case of fourth wire system. Okay, main feature is reactive power compensation in PFC mode as well as the zero voltage regulation mode. Means this device is going to operate two mode. First one, you can maintain the AT power factor. Second case, you can maintain the zero voltage regulation. And again, this device is going to operate at PWM switching frequency. Means you can take somewhat medium switching frequency, carrier based, maybe carrierless, that depend upon your processor, what processor you have used, based on that. Okay, here you can see these are the features. Okay, now features of the whatever selective filter are there. Next is mode of operation. In case of PFC mode, we are able to maintain the zero angle between current and voltage, supply side. We are not going to deal anything in load side. In case of voltage regulation mode, we are going to see somewhat slightly leading power factor angle, because we need extra reactive power to maintain the PCC voltage at rated value. Due to requirement of extra reactive power, we are going to see somewhat leading power factor. Why leading power factor? Because we need somewhat extra leading reactive power. Why we want that one? Because we want to maintain PCC voltage at rated value. That is our requirement. Okay. At a time only one mode we can operate. Performance. Here performance means function depend upon the topology, and performance depend upon the control. Function means if you want reactive power, you want harmonics, you want load balancing, those phenomena depend upon the topology. And effective utilization, effective performance, or maybe you can say dynamics, depend upon the control. And also switching as well as their switching frequency. Again, I will tell here. Maybe you can say, suppose you have a 2 leg converter. You have a only you can solve 2 problems: reactive power and harmonics. If we have 4 leg converter, you can solve all 4 problems. If we have a 3 leg converter, you are going to solve only 3 problems. That also we can say in that sense also. So in a case of discrete, many topology are, many control are there. So we will discuss one of the basic control. That one we can use to compensate the reactive power, harmonic, and unbalancing. In case of PFC mode, as well as the ZVR mode. Okay. Again, how we can select the controllers? That depend upon what type of performance we want. In this case, we are telling independent controller for 3-phase we want. Here, due to that one, we have used single phase PQ theory based control, because I want to control three individual phases independent. So due to that one, we have used this technique. So then we can say control advantage. Again, whatever thing you want to develop, in that cases, we need to know what are the advantage, why we want to design, what is the requirement. If we know these 3-4 points, then we can develop some new thing. But here I want to design only one old control only, whatever control already published in papers. Those already you can see in books also. So in that case, need a high convergence speed. We should have high convergence speed. Independent controlling are 3 phases. The structure of control is based on the basic arithmetic operation only. Due to these reason, its implementation in software and hardware is somewhat simple. Means if we have a control, that control based on the pure mathematics only. We have very less assumption. Suppose 5 logic maybe no network those side. In those cases, we are going to get robust response. But in that case, mathematics is less. Only based on the previous data, the system are going to work. But here, total everything depend upon the only calculation. Due to this one, its implementation in software and hardware is somewhat simple. So we can see this 4-leg this is a 4-wire system, three single phase and 4-wire. 3 single phase system you can see. 1 phase, B phase, C phase. Then we have a load and also we have supply source. Now, what are the main thing that I want to tell here? Other theory you can read from books also. Here main thing is there. By this transformer, we want to compensate neutral current. This is a passive arrangement. By simple transformer connection also, we can compensate the neutral current. Okay. But if you want active compensation for neutral current, then you can design 4-leg converter. But here we have a 3-leg converter only. By 3 leg, you can solve 3 problems: reactive power, harmonic, unbalancing. Okay. First requirement is you can maintain DC bus voltage at least peak value of line-to-line voltage. That is our requirement. We should maintain this DC bus voltage at least peak value of line-to-line voltage. That much you can maintain. Okay. After that, also we should design value of capacitor based on the energy balance formula. Formula is 1/2 CV square equal to whatever energy you are going to see in output of the converter. Energy at output of converter is 3VI. This is the power into T. T is the recovery time, with time taken to recover the DC link after any disturbance. Okay. Also, we have one RC filter. That RC filter is going to provide low impedance path after half of the switching frequency. After half of the switching frequency, RC filter is going to provide low impedance path, so that whatever switching noise are there, those you can put towards ground, and we have a clean supply voltage. Okay. And to fire this IGBT, we need control. That control you can process inside the processor. What type of processor you have seen? Maybe DSP, microcontroller you can use, DSP you can use, or maybe you can use also advanced processor, means RT-Lab you can use, maybe that D-Space you can use, maybe you can use any low cost processor also we can use, 500, 600 rupees low cost processor also we can use. Whatever that depends upon the amount budget. If you have a very high amount, then you can use somewhat high-end processor. But if you want to do research work only, then you can use high-end processor. If you want to do some development work, such just only development and design, commercial application, then you can do somewhat 500, 600 rupee processor you can take, then implement that one. Means we have a two end. One is the research point of view, second one the development point of view. Means if you want to develop the system for market purpose, then you can use at least 100, 200, 300 rupees, 500 rupee processor. If you are going to use for research application, then in that cases we need to see response, we need to report those things. Also, if we are going to use sequential processor, that I microcontroller, those things, then in case of operation is sequential, and if we are going to use FPGA based processor, operation is parallel. In case of sequential processor, we cannot say our system responds very fast, because already people are knowing that system is going to perform by sequence operation. But in case of that FPGA based processor, if that operation is parallel, in that case we can say our system is fast. But in case of microcontroller microprocessor, in that case we cannot say our response is fast, because process is purely based on the sequence based only. That is also main point. Also, if we are going to use DSP, so DSP also sometimes some cases we have a sequential operation, some cases we have a parallel operation. Okay. Also you can see what are the facilities inside of this processor. Number of ADC, number of DSC, as well as the gain tuning sliders. If gain tuning sliders, those things are there, then cost is somewhat high. That point also we should see. Okay. Then next point is how we can decide the power rating of these converters. Power rating means whatever voltage source converter you are going to take, how we can decide the rating of that one. Rating based on the types of function, rating depend upon the what type of function we want. If I want only reactive power, I want only harmonic, I want only unbalancing, I want all four power together at a time, then in those cases rating are going to increase very high. And also whatever rating by calculation you are getting, based on that one you can put somewhat 10 to 50% extra also. Okay. And always we can design system based on the highest kVAR rating requirement. If your highest kVAR requirement is from reactive power only, then based on the reactive power you can design. We can assume that we are not going to face all these problems at a time. So maybe for other person also our system is going to work. Okay, so in design stage we can remember what type of function you want. So based on that one you can design the kVA rating of the converter. Here we have used 25 kVA converter with load is our 35 kVA. I have used 25 kVA converter with 15% extra reactive power. And DC-link, how we can select DC-link? That formula they have given. But basic theory is we can design DC-link based on the peak value of peak requirement of line voltage. Means you can see peak value of line voltage. Based on that one, you can decide the rating. Means we should select DC-link voltage at least peak value of line voltage. From that point, our system is going to work as a capacitor. For sufficient operation, we can use 2 V line to line divided by root 3, that formula. Based on that one, round figure, whatever calculation, whatever you are getting, that one you can use, and after that you can make round figure. Okay. Then we can decide the kV rating, the DC-link capacitor ratings. So first you can see energy balance formula. Based on the energy balance formula, you can find out the value of capacitor. But rough guideline is for each 5 kVAR requirement, you can put 2000 microfarad. Again, we are going to use electrolyte capacitor only, because in that range, only in case of high capacitor range, high microfarad range, those are available only. So we are going to take electrolyte capacitors. After that, also we can say we can take somewhat overloading factor as well as the energy variation due to dynamics. Those points we should consider. So our rough guideline is for each 5 kVA, we want 2000 microfarad. Also, we can design value of DC bus capacitor based on the DC side, based on the DC side calculations, and percentage value of ripple DC bus voltage ripple. Okay. Then here we have assumed that in our system have only 0.5 to 1% ripple. So whatever rating you have, rating 25 kVA, DC voltage how much? 700, 35 ampere we are getting. So 35 ampere divided by how much? So 35 divided by 2 divided by 2 pi into f mean 50 into into 5. So based on that one, we are getting 10,000 1.25 microfarad selected value 10,500. Again, you can see the market condition also. Maybe we will not get 10,500. Maybe 11,000 you can get, maybe 9,000 you can get, maybe 15,000 you can get. If you are going to put some high value of capacitor, means that is not a disadvantage, but that is not this one in terms of performance. We are going to see somewhat smooth performance only, a steep performance. But second side, disadvantage is cost is high. And also we need to design the value of inductor between converter and PCC. Those you can design based on the whatever formula we have given, root 3 MA VDC divided by 12 alpha switching frequency and repeat on the compensating voltage. So based on that one, you can design the value of interfacing inductor. Or that inductor has a responsibility to maintain the flow of power from line to PCC, line to PCC point to converter point. Okay. So based on and also this one is going to smooth the value of compensating current. Good point we can see. And rough guideline is if your load current is almost support near to 10 ampere, 8 ampere. So and supply voltage maybe you can say 110 volt or maybe 200 to 30 volt. In those cases you can take 2 to 3 millihenry any value you can use. But formula is this one. Based on this one we can design. Already we have seen the value of what is the value of RC filter. RC filter is going to ground the switching noise superimpose in PCC voltage. So due to that one we have used RC filters. Again, IGBT and that IGBT can rating and voltage, how we can decide? That one depend upon the voltage, depend upon the total DC bus voltage plus percentage overshoot. So we have taken 10% overshoot. So 770 we have got, but cost of 770 volt IGBT and 1000 volt IGBT nearby only. So in that case, maybe you can say some higher range only. Maybe you can say 1000 volt IGBT. That is not a problem because we will not get maybe 770 volt DC IGBT. Maybe they are going to manufacture maybe 500 volt or 600 volt, maybe 700 volt. Maybe you can say 1000 volt, maybe 2000 volt in that way. So maybe you can take that. And current rating also based on the 1.2, 1.25 in bracket. Supply current peak value plus ripple component. So based on this formula, we can design the value of IGBT devices. So maybe you can use particular, maybe you can use what we can use. Particular means IGBT you can select from particular manufacturers and you see the rating. Based on that, you can use. Here we have used semi-convex somewhere 1200 volt, 2000 microfarad, 2000 ampere. That is not a fix. You can use any company. After that, we have any question till now? Hello?
No, sir. You can continue, sir.
Okay. Now you can see we have just for understanding purpose, we have put on basic control so that we can understand how this one is going to work. So this capacitor we are going to operate that in direct current control mode. This is the main thing. It means indirectly we want to control the current. Indirectly we want in this case we want to generate the reference current. The reference current we want to compare with actual current. That error by that error we can generate the gauge signal. This is basic theory. So in this case, this is a whole arithmetic operation, arithmetic view. How we can design. So you can see DC link. First you can see the DC link. You can sense put PI controller. Tune the value of KPKI, then you can name that output of PI as some value of power, PDC. Some name we have given, not PDC only, some name you can give. That is signal. If your whole calculation is based on the power, you can put power. If whole calculation is based on the current, you can put current. If whole calculation is based on the voltage, put voltage. And we should find out the power at individual phases, phase A, phase B, phase C. For active power, 1/3, this one we need for. Why we need 1/3? Because we want to make load balancing phenomena. Upper loop only. If we are going to use only upper loop, then our system is going to work in PFC mode. If we are going to use lower loop also, that time this system is going to work as a PFC as well as ZVR mode. Means first you can run the system in PFC mode, then you can run system in ZVR mode. That is point. Okay. In case of ZVR mode, again you can whatever PCC voltage you want to put, whatever value of PCC voltage you want to put, that one you can put as a reference, and sense value of VT you can take, compare, put PI controller, tune the value of KPKI. After tuning the value of KPKI, you have a Q, some QC, some name you can give. That one you can add with average value of load reactive component. You have a total QT, find out the value of reference current, that active value of reference current, and passive and active value and active power component and active power component of reference current you can add. You have final value of ISA, ISB, ISC. Very basic theory only. That one is useful for maybe for learning purpose only. After that, after adding active and reactive component, you have ISC star, ISB is ISC star. Then you should also send the value of supply currents. Then you can compare supply current A, reference current A from supply current A. Then you will get error. That error compare with triangular wave or maybe carrierless signal. After that, you will get one gauge signal. That gauge signal you can give respective phase leg first IGBT. And the same signal you can pass through not logic and you can give to respective phase leg lower IGBT. Okay. Same way you can do for phase B and phase C. Means here in last section is depend upon depend on switching scheme. What type of scheme you are going to use to generate the gauge signal. Based on that one, you can design the signal. This is one case. Second case, suppose you want to generate gauge signal based on the direct current control. So for that one, directly you can generate the compensating current. I can fit to system. Okay. Next is these are the whole means how we can find out the active power, reactive power, those things we have given. Phase A active power, phase B active power, phase C active power. Again, pointer there means whatever voltage there directly you can feed to that one. You can consider alpha ABC. 90 phase shift you can consider V beta ABC. Then you can multiply. Same way current also. Direct component directly whatever component coming that one you can feed to. That one you can use to calculate the value of QLA, QLB, QLC as a alpha component. Beta component you can use after 90 phase shifted. Okay. Next point is this one. Okay.
Okay, sir. I will. Please, participants, switch off your video.
Next point is why we want 1/3. So you have power 1/3 we want to find out the average power. If we are not going to make 1/3, in that case we are not able to get the load balance. We are not able to maintain the supply current balance. Okay. So for balancing phenomena, we need 1/3. And after that, total value you can find out. So how we can find out what are PI output are coming? That output you can add with average value of active power component. Means how we can get PDC? First, you can tune the value of KPKI. You have a minimum constant DC, tune the value of KPKI. Output of PI you can maintain minimum constant DC, and same time your HO value should touch the reference value. If we are going to see these phenomena, that one you can use as a PI control output. Point is, put the value of KPKI. If your actual value going to touch the reference value without any oscillations, in that condition, see the PI output. Maybe in that condition, PI output is minimum constant DC. That one you can use as a output of PI controller. That one you can add with load active component. Okay. Then similar case for the PCC terminal voltage PI, you can tune the value of KPKI again. You can maintain the required PCC voltage, and output of that one you can consider as a QC. Some name we have given. Then maybe you can give another name also, no problem. After that, you can find out the value of ISC star, ISB star, ISC star using this formula. And this is a well-defined theory only. You can get from any book or any papers. After that, you can sense you have error. Now you can amplify this error because this error is somewhat less only. After amplification, compare pass to the PI controller. PI means you can use only P controller, not I. Just I you can put very small value. I want to amplify that error component. Okay. Then compare with 10 kilohertz or maybe less than or maybe more than that carrier signal to generate the gate signals. These are the, maybe you can say these are the some data how we can do the simulation work or maybe implementation work. You can see how we can plot the curve in PFC mode. We have maintained the distortion near to our IEEE 519. Load side you can see distortion how much 40.46. Supply side supply volt distortion also we should see. This is a common thing only. Also you can see 0 voltage variation, load harmonics, supply current harmonics, supply voltage harmonics. Now I will tell 2-3 lines here. Here we have recorded the result using under non-linear load. Under non-linear load in PFC mode. Non-linear means you can see our supply load current is that just you can see. Load current is just like a square wave near to that. Then supply current how much? Sinusoidal with how much distortion? Near to 4.5, this percentage. And we have compensated this harmonic from how much? 32% to 4.5, 37 to 4.4, 33 to 4.3. And the same time you can see nature of compensating current and voltage. Nature of compensating current, supply voltage distortion and nature of neutral current. So in this case, what type of conclusion we can make? Since we have run the system in PFC mode, our PCC voltage going to D. So at no load condition, PCC voltage how much we have taken? 160 volt. After compensation at loaded condition, we have put the system under load. We have connected the loads. After loading, we have flow the current 6.53. That time how much voltage had dip? We have observed dip in voltage how much? 160 to 152. Now I want to maintain that 152 to 160 again. So that is the ZVR mode. You can see here, in case of ZVR mode, along with reactive power, harmonic and load balancing with neutral current. You can see just only our supply current has increased. Same time you can see our power factor, the first case power factor how much? The first case power factor may be voting only. Second case we are going to see power factor somewhat leading. That's the difference between PFC and ZVR mode. At a time only one mode we can operate. Both modes we cannot operate together. Okay. Means after ZVR mode, suppose I want to manage PFC mode, this is somewhat typical only. That will take so much time. If we want to remove the VT loop, that will take time. They are dynamics. We can regard the dynamics in DSOs. Then you can see also the load balancing phenomena. Here you can see what meaning of load balancing means name is load balancing, but we are going to balance the supply current. That is meaning. Name is load balancing, but we are going to balance the supply current here. You can see at one phase we have put how much load? 0 load. We have removed the load in one phase. Okay. Due to your removal of load, what type of problem we will get? Our two phases are going to become overloaded. One phase is going to become underload. But up to some level, that is not a problem. If that problem is going to continuously increase, if that problem continuously going to increase, then maybe your two phases are going to become heavy loaded. Maybe also they are going to burn due to this overloading. In that case, we should maintain the balance, all three phases. You can see our supply is balanced. See the figure 1, 2, 3. Figure A, B, C. Okay. In case after balancing, you can see in case unbalanced 5.5, 6.7 and 0.0 something. After balancing in the all three phases, we have a near to 4.5 ampere current. These are the some basic features. In that way, we can design the resistor filters. Now we can see how we can design. So here we have designed whole system based on that processor. So that D-104, we have this work we have done maybe 2015 only by one MTech student, and after that we have developed whole system at somewhat 230 volt now. Previously we have developed 30 volt by some small converter only. In that case also we have developed the using 6 IGBT. Whatever IGBT we are getting from shop now in the Surat market, based on those IGBT we have developed the one 30 volt line to line capacitor. Means at 30 volt also we have operated. That is meaning. Okay. And also depend upon according to your sense signal, you can decide the processor. Maybe you can see the ADC, DAC, those points also you can see. If you have a sufficient maybe required number of ADC and DAC, then you can use those processor. Means how we can select processor? First is speed. Before that you can see the ADC. If you don't have ADC, sufficient ADC, that is not useful. No? Then first we can see those points also. Then these are the, previously we have checked this one. In many cases we have damage in some IGBT and those things, then we have. And also if we are going to develop the converter with their diverse circuit. So if we have, in that case, if you don't have it, that you can say, if you don't have dead band circuit, or maybe delay time between same leg to IGBT. We need somewhat delay time 2 to 5 microseconds dead time. If you don't have, then chances of short circuit is high. From DC link, DC link is going to short circuit from this leg. If device change is going to take place, face same leg, upper IGBT conducting, if that one going to off and lower IGBT going to on. Between that one, we need some delay time. How much? 2 to 5 microseconds, maybe near to this one, maybe somewhat higher also, no problem. If we are going to take more higher value, then your PWM paths are going to miss, maybe some performance are going to deteriorate. That is disadvantage. Here we have developed this delay circuit using IC7400 NAND gate, and we have created somewhat 2.5 microsecond delay time. So we need to develop. This is a small converter, auto converter we have initially at 30 volt. So due to this one, we have taken the result at 30 volt only in the year of 2014 and 15. Initially we have tested. This is RC filter, but RC filter when 30 or 40 volt RC filter had no much role. After 100 volt or one, or maybe after 60 or 70 volt, now your RC filter is going to become RC filter is going to play major role. Even in 130 volt or 150 volt, or maybe in that range, RC filter has much impact on the system. In this way, you can design somewhat shunt filter. Okay. Next one. Suppose you want to design series filter. How we can design? Then I will tell application. Okay. After that, series filter. Suppose you want to compensate the why we want series filter, or maybe you can say DVR. Advanced version of series filter known as DVR. You can say. Basic function of this one is to compensate the sag and swell. Additional feature are reactive power compensation, as well as the unbalancing and notching and those you can interruption compensation of interruption. So again, we have many topology. In this case, maybe three-phase wire system you can use, maybe three-phase wire system you can use, maybe with split capacitor, matrix converter, multi converter, many other you can see detection. So many things are there in this area also. Till now we have one control subtopology, means 3-leg topology and 6-leg topology, and application some control and optimization technique for tuning up PI gains, KPI gains. those system we have developed and that system is working also. Assume that again this system may be two types. One is based on the energy source, maybe based on the DC link. Okay, DC link you are going to generate the compensating voltage coordinated with line current. But in case of that energy based system, you are going to generate the compensating voltage in phase with voltage. In phase with current, you can say if current and voltage both are in same phase supply current. In this case, we want to maintain the rated voltage at load terminal, not supply terminal. Supply we are not going to correct. But in case of shunt filter, we are not going to correct the load, we are going to correct the supply system, supply source. That is the advantage. That is person you can say. In case of series filter, we want to maintain rated voltage at load end. But in case of shunt filter, we want to maintain reactive power harmonic free current as supply end. We are two different pictures you can see. My topology you can see. Here I want to tell so this is the main thing. We have three types of compensation. One is the quadrature, second one in phase, third one the between quadrature and in phase. All three types of operation you can operate by developing the control only. So maybe you can say DVR P, DVR Q, DVR S. P means active power, Q means reactive power, S means apparent power. So based on that theory also, you can say how we are going to develop this system. Okay, there is the operating mode only. Again, in this case, maybe you can use time domain algorithm or maybe you can use frequency domain algorithm. Both types of system you can use. So maybe in frequency domain also, we classical transform and adaptive base. In time domain also, maybe you can use based on the mathematics, basic mathematics, maybe based on the transformation, or maybe based on the adaptive theory or artificial intelligence, those things. Then, in case of shunt filter, whatever reference we have taken that problem in current and reference we have taken as a voltage. In case of a series filter, you can take reference as a current, problem in voltage. Okay. So by reference voltage, by reference quantity, you can generate the template, or by using that template, you can generate the required gate pulse, required reference voltage. By that reference voltage, you can generate the required gate signal. How we can generate the reference voltage? That formula is there. That is, first you can find the fundamental voltage. Whatever PI output are coming from a DC link voltage, DC link capacitor or DC link loop, so that one you can multiply with in phase template. VT output means PCC voltage, terminal or maybe AC bus voltage output, AC bus voltage PI output, multiply with quadrature template. Okay, so fundamental minus VDCE into UA plus VTE you can say into UQA. In that way, we can generate the required load reference voltage. How we can find out VT? You can use basic formula 2/3. All those whatever formula is there. This one you can use as a reference. This one you can use as a sense value. A reference you can select according to your choice. Again, we can use this clock transformation and path transformation. Based on that one, we can play here and there. So you can see this is our basic circuit diagram. Supply voltage, load. This is a converter. In this case, we need to see this one. Suppose how we can generate the gate signal. Just you can see 2 minutes, then I will discuss. See the diagram. Maybe this one we can take from any paper. Some online paper are there. Based on that one, maybe you can read also. DVR based on the SRF technique. Just you can put in Google, design of DVR using SRF control. The very basic control for understanding purpose only, then we can design. In this case, what we will do, First you can first we can sense the DC bus voltage. You can sense how we can sense. You can use sensors. On MATLAB you can use a voltmeter. After that you can compare with actual reference value, put PI controller, tune value of KPI, output of that one you can consider as a V loss. Supply voltage you can sense, convert ABC to DQ, whatever value are coming, remove the oscillating component. And you have a somewhat average value of refill free value of VDDC. Same way you can do for reactive loop also. You are going to get VQDC. Okay. After that, you will get the also you can sense value of load voltage and amplitude. Put some reference value. That my voltage I want to maintain. Compare with PI compare and put PI controller. Tune the value of KPKI. You have a VQR. Okay. After getting a modified value of VD star and VQ star, you have a VDQ. Either no, D and Q you can convert to ABC, and you have a VLA star, VLB star, and VLC star. Okay, but in these conversions also we need information about the sin theta cos theta. And when you can put one reference here, we are going to put load current as a reference. Load current you can sense. After that, process inside the PLL. Output of that one you can consider as a theta. You can put sin theta cos theta. Then you can give that information to ABC to DQ and DQ to ABC conversion. Okay. Then after that you have a gauge signal that reference current using those reference voltage. Using those reference voltage you can generate the gauge signal in indirect voltage control manner. Again, using this gauge signal you can generate the gauge signal using this reference signal. Generate the gauge signal based on the indirect voltage control principle. Okay. Next is see the response. Here we have treated the sag. First we have a normal voltage. Then we have a sag. Then again we have a normal voltage. Then swell. Then we have normal voltage with distortion maybe between that. After that we have unbalancing. Then we have a normal voltage. The meaning is there. If you are going to get positive sequence fundamental component, if you have only fundamental component, then by that one maybe you are going to compensate reactive power harmonics only. Reactive power, harmonic and check swell. Reactive power, harmonics, not reactive power, sex swell and harmonics. If we have a fundamental positive sequence component, then you are going to compensate the unbalancing also. So those you can observe in load voltage V L ABC. Here also you can see after 0.9, after time t equal to 0.9, our requirement to see how much time is going to take the recover the DC link. How much time is going to take how much time device is going to take to settle the value of load voltage. So we need response within half cycle or maybe less than that. So that response time also we should record. We should find out. Same time also we can see condition of PCC DC bus voltage. How DC bus is going to vary, and value of terminal voltage. And if due dynamics, see the condition of DC link. If DC bus is going to change and again going to return at reference level only, then you can say your PI is going to act. PI is going to work. Hello? 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 Okay. Second case, also we should how we can check, that is point. How we can check our PI is working or not working. See point? See here, point maybe 6.5 somewhere. We have created the set. And see, our DC was also going to change. After change, that has got some value, maybe 10 or 5 volt star, and again have returned back to reference level with some oscillations. Here means value of Ki is somewhat higher. Not higher, you can say some oxidation there, na? Means maybe we are not able to remove the oxidation by Ki. So maybe we need to tune the value of Ki here. Same time you can see condition of AC bus voltage. If your actual value of that Vt is how much? 3 near to 330 you can say, or 340 maybe you can say. If that is that if we have a 340 volt PCC voltage and amplitude, and we have after tuning that voltage has gone, means doing say that voltage has increased, and that is not returning towards original value, then that is problem of PI only, not a problem of control. We need to tune the PI that should return towards reference level. Here, that one not reaching, that one not going to return reference level. It started returning, but again after some time this has increased. This is the problem of PI only. PI tuning means we don't have a proper PI tuning. So and also we cannot make proper PI tuning by random trial and error. So for that one we need to develop some algorithm. How we can do the PI controllers, so that we have some good response. We should know at least guideline how we can put the value of KPKI. Otherwise, some random value you can put, that will take me 1 day, 1 week, 1 month. That depends upon the how we are going to tune the value of KPKI, how we are going to put the value of KPKI. To reduce the time, maybe we can develop some algorithm for tuning of KPKI. You can see, in this way we can record the response from any controller. How much time is going to take the recover? How much time is going to take the system to recover or to maintain the load voltage near to rated value? Okay, see the response. First one we have supply voltage. After that, supply voltage due version, then load voltage, then load voltage due version. So these we have used some method based on the optimization, and we have got the response. How and what ways we can find out the response? You can find out setting time, rise time, fall time. What are basic controller there? By that you can say our system is correct. Okay. You can see these are our experimental result, our experimental setup, and by that one we have recorded the result. Due to we have compensated our voltage based power quality problem using DVR. These are our whatever processor we have used, that is the microwave box. Sensors we have used, we have developed in our lab, and converter we have taken from outside, right? 25 kV converter we have taken. Then also we need to maintain the isolation between power circuit and control circuit. So you can put some isolations board, and also we need to convert, we want to maintain gate voltage according to converter requirement. So for that one, maybe you can use transistors, you can amplify, and also we cannot connect that what we can say, control and power circuit directly. For that one, you can put isolation circuit. Here we have put isolation using 6N130C, that is optical isolator, and by 2N 4 times 2, by that transistor we have used amplification. Our that is whatever converter we have used, that converter is going to 13.75. From above this point, our converter is going to act as a, our converter is going to fire. Our converter IGBT is going to turn on. And you can see after many trial error, we have set the value of this RC filter. Now in this next point also you can see, these are the, always we are telling we have an injection transformer. These are the injection transformer to inject the required compulsory voltage at load end. Also, if we don't have sufficient value of inductor, then we can add some extra value of inductor also, so that we have a compensation. We have a proper compensation. Okay. Clear? One more thing is there. This is the one of the new area you can see. In this portion, maybe we can work. Somebody want to work here. Also, application of these in maybe dive sector, maybe some other sectors also. Now we want to see some application in wind farm. Now, okay, what the conclusion? Here our conclusion is, by using DVR, we want to compensate voltage side, swell, unbalancing. And also, we want to record the result according to system requirement. We don't want the result. We don't want response after 10 seconds, after 20 seconds, after 1 minute. We want response within microsecond or within a half cycle. Will be the right one, so that our system should not experience any delay. If our supply is gone, so that system automatically should switch on and without any delay. Those type of system we want. For that one, we need to design some. We should have some perfect or maybe proper value of proper develop proper selected value selected control algorithm, as well as high performance IGBT or maybe power devices. Okay, so those things we should see. Due to development of power electronics as well as the processor, this one is somewhat more easy. So based on that one, maybe you can develop something. Maybe you can say PL based, or maybe something you can say circuit theory based, or maybe you can say here classical calculation based method. You have developed. Now next point is application of that induction generator. Application of that shunt filter in wind based energy system, wind based distributed power system. You can say like that. In this case, we want to generate power at local end. Or maybe at local end, we want to generate power. Any place, maybe coastal area, maybe sea area, coastal area, maybe hill area, maybe any rural area you can say, place where we don't have power. But in that place we have wind. We need wind only in that place. In that places, you can put some turbine, 1 kilowatt, 2 kilowatt, maybe less than that, more than that, depending upon the conditions. Or maybe 5 kilowatt system you can develop. Here we have developed system based on the system rating is 3.7 kilowatt, 5 HP motor. And we have emulated property of the wind turbine using induction machine only. We have taken two induction machines coupled. One induction machine 440 volt, 415 volt, maybe 5 HP. Second one 230 volt line to line and 5 HP. Okay. Both are 5 HP, but we have created difference in line voltage. One case line voltage 415, second case line voltage 230. After that, And that second 450 volt induction machine we have connected to VFD. And that VFD we have connected to supply system. Now our objective is to emulate the property. So maybe you can change the frequency. You can maybe 50 to 49, maybe 48, maybe 52. In that way, you can change the frequency. You will get the speed variation. Even that speed variation also, we are going to get somewhat smooth, somewhat 50 hertz, 50 hertz frequency at output side. Even we have variation in frequency. We have 50 hertz frequency as well as the rated voltage. In this case, I want to maintain rated voltage at rated frequency, along with reactive power harmonic and balancing and neutral and compensation. That is the main point. Any question? Okay.
No,
Again,
sir. You can continue, sir. Continue, sir.
again, in this case also, we have taken whatever system initially we have taken a 4-wire system. Same system we have taken. Okay. Now point is there. Here, this is the main thing. These three equations. What are equation you have seen in G.K. Dubey book, electric drives, or maybe any other book. So you can see we have a 3 torque. One is load torque, machine torque, and turbine torque. Mechanical torque, electrical torque, and load torque. Here load is static. If all 3 torque are equal, then no problem. Again, turbine is going to run motor according to Tm only, and generate the Te. If T equal to TL, then also no problem. Okay. Turbine is going to run that second machine generator by some speed are going to create a TE. If T equal to TL, then we don't have problem, and we are able to maintain the voltage frequency at rated value by some capacitive arrangement, some passive filtering arrangement. You can put some excitation capacitor, you have a response. Okay. But second thing, when our load is going to change. Okay. If load is going to change, what is the point? If load is increased, then our voltage is going to dip, frequency also going to dip. Second thing, if load is decreased, our frequency and voltage both are going to increase and decrease. Okay. In those cases, we need to maintain voltage frequency fixed along with reactive power harmonic compensation and unbalancing. Also, this is one case. Second case, suppose our supply side wind speed is going to vary. Then we need some energy storage element also. Whatever energy storage element we have discussed in DVR, by that one, what we can do? We can, if battery we are going to use, then that system is going to compensate. That system is going to generate compensating voltage in phase with current. If current and voltage both are in same phase supply side, your converter it is going to decrease. That is the advantage of energy storage element. Energy storage element as a battery. If we have energy storage element as a capacitor, that is also one storage device. In that case, we are not going to inject compensating voltage in phase with current, or maybe supply current, you can say. In that case, injection voltage is quadrature with that one current. Okay. So those phenomena you can see. Okay, point are there. If TE and TM, if TM is going to vary, so a small fluctuation are there. And if T is sufficient to generate, if TM is sufficient to generate required value of TE. Required value means we need to generate 3.7 kilowatt. Then some fixed value is running. If turbine is fixed speed, then you have fixed power. If turbine is going to vary depending on the wind speed, then you have a different value of power. Then whatever power fluctuation you are going to observe at generator end, that one we need to manage somewhere. Okay, we need to manage somewhere. Where we can manage? For that one we need again energy storage element. Energy storage element means you can use maybe battery. Battery means battery have property. If small fluctuations, maybe 0.2 kilowatt, 0.1 kilowatt, maybe 500 watt, those type of things, fluctuations are there, then battery is going to store the power. Battery is going to charge also. One case. Second case, if same thing happen in load side also. Suppose your load requirement is high, but data is not going to give, then battery also going to provide somewhat extra power. This is the second phenomenon. Okay. Third thing is there, if we have somewhat higher generation due to wind speed high, then what type of thing we will get? Generation is high, but load demand is less. Then up to some level, battery is going to store the power also. Then battery is going to play major role in case of wind farm. In case of wind farm, battery is going to play major role. Okay. In that way, battery is most common in case of wind farm. But in case of hydro farm, small hydro generation, or maybe you can say small hydro power plant, those cases we are going to assume that our input is constant. We are going to maintain the water flow somewhat constant by some arrangement in what we can say hydro power plant. In that way, in that case, we can use capacitor. If our water flow is constant, but here even we don't have any small basin also. But in case of wind, small basin we cannot take care. For that one, always we can use battery only. Otherwise, you can use some small extra load, extra dump load to dump the whatever extra power is coming, so that our system should not damage. This is a basic theory behind this wind farm. Okay. Now we will see. Okay, and whatever battery we have used with that voltage source converter, we have many features now. This whole converter is going to work as a voltage frequency controller, as well as the reactive power compensation, harmonic eliminator, unbalancing, and neutral current also we can compensate. So these much function we will get. Okay, now. So this system have many advantages, you can say. Okay. Any question at this point? This is the main story here. Next is, now everything we have written. J is the moment of inertia of turbine, H is the inertia of a constant of generator, omega is the mechanical speed, T is the rotor speed, those are that. Tm, TL are the mechanical torque, load torque, electrical torque, those things are written here. So basically that whatever I have told now, that is main thing. Based on that one, we are going to maintain our system efficient with less losses. Whatever control we can use here, we can use this type of control. Whatever control we are going to use. Initially also we have seen, in case of DVI also we have seen this control. So we can compare actual frequency and reference frequency, put PI control again, output of that one you can consider IDC, because we are going to convert load current as a ABC to DQ. So D you can use output with D you can add the output of frequency loop. With Q you can with Q from QC you can separate load reactive current. After we have modified value of the SDSQ, convert ABC to DQ, then I have a load reference current. Okay, here we are going to use this system for. Here this one we are going to use this system for compensation of current-based power quality problem. Okay. Since here we have problem in load current only. So voltage you can set as a reference. Again, main thing. In any type of controller. Okay. Hello. हाँ हाँ मुझे फोन कीजिए अभी 3:30 बजे, क्योंकि मैं क्लास में गया था, मैं 3:30 बजे वहां जाऊंगा सेंटर में. ठीक है. Okay. So now point is, what is the requirement of this LPF filter? Because we want to reduce the oscillating component. We want to block the oscillating component. To that one, they have used this thing. Okay. Then how we can do KPK controller? Already I have told you can compare to means generate that VT as equal to VRT. If both are equal, then in that condition we are going to get minimum constant PI output as a minimum constant DC. Then after that you can do whatever you want. Here, for compensation of that neutral current, we have used transformer, delta star transformer. The delta star transformer you can see based on the PQ information of generator, you can design the value, find the value of ISA. Based on that ISA, you can design the value of load neutral current. Load neutral current how much? Maximum value of neutral current is √3 into IL worst condition. Then based on the worst condition, you can design the rating of the transformers. Based on the primary and secondary side VA rating divided by 2. Based on that theory. Here, based on that theory, you can design. Now next is, and in case of next point is, see here, in isolated configuration, current flowing through the transformer is sum of the neutral current and current supply from the converter of the, okay, these are the how we have designed. So whatever basic theory we are knowing now, that transformer, the primary side V1 I1 plus secondary side V1 V2 I2 divided by 2. Based on that one, we have designed this. Okay. So based on that one also you can design. Here frequency of here neutral current how much? In normal condition neutral current equal to load neutral current at normal condition. In case of unbalanced system, in case of you can say non-linear system, if system is balanced with only linear load, linear inductive load, in those cases at balanced condition we have a zero neutral current. But in case of unbalanced case, how much current we are going to observe? That can maybe IL into √3. Okay, so that much current we can observe. Okay. So based on this neutral current theory, now you can develop your neutral current compensator, maybe active, maybe passive. In case of active, many transformers there, transformer connection you can make. In case of passive, in case of active, based on the IGBT, based on the converter you can design. Now you can see how we can develop setup for this one. The setup you can see here. You can see this is the machine. What a machine we have used to two machine we have used, coupled with two machine are coupled. One work as a generator, second work as a motor. The motor plus that machine work as a motor with this VFD. Those work as a turbine. The second machine work as a generator, that supply we have taken PCC, and with this also we need to put the capacitors, so that whatever receiver voltage are there, that voltage we are able to develop, we are able to boost up to certain level. After that voltage you can give to load. Here we have the other inductive load capacity, the other inductive that resistive load. These are inductor, RL load, rectifier with RL load. Those you can develop whatever thing circuit connection are there. And after that, what are problem you are going to get from these rectifiers? Those you can compensate using this voltage source converter. We have voltage source converter with the sensing circuit and this interfacing inductor. Based on that one, you can compensate those problems. Okay. Now in the whole this setup, this supply, this one we have connected to our normal grid supply. Next one is, now main thing is in whole this setup, point is how we can design sensing element and how we can connect those elements to processor. Then you can see, you can sensing element, voltage sensor, current sensor you can design connect to your ADC. So BNC cable you can use. By BNC cable you can connect. In BNC cable means one main is there, one ground is there. So by that one you can connect to your processor. A processor output is going towards your control desktop computer. So now input here we have this one. Each sensor also want certain voltage of excitation voltage. Here LV25 we have used, that LV25 also want 15 volt plus minus. So 15 volt plus minus you can give to power supply only, and you can convert that output of that sensor based on your ADC voltage. If your ADC is unipolar or bipolar, based on that one you can convert. Since our this process, what a processor we are used, those are bipolar ADC, means plus minus 10 volt we can generate. Input how much? Input is 50 ampere, 50 kilo ohm. Watt also you can find out. So based on this watt and that resistance, you can find out you can say the resistance. You can see based on data sheet 500 volt they have given, 10 milliampere, 500 volt, 10 milliampere, 50k we have got. If we are going to operate at 500 volt line to line, then we are going to see 10 milliampere, so 50k. But we are not going to operate 500 volt. Maybe we will operate 330, 230, 330, 440. So always we have safe side only. Power rating how much? So you can find out power, 5 watt you will get. You can sell 50 kilo ohm, 5 watt. Output side, output voltage, I want 5 volt, current how much? 25 ampere, then 200 ohm you can take. 200 if you will not get, you can take 270. Near to whatever market, whatever you can see in market, based on that one you can select. Further, calibration of voltage also required. Then voltage output how much? Voltage power, what it is? 270 and 225. 270 to 25. Milliampere. 270 how much? Resistance into current. Okay. So we are going to get 270 volt output. Say 6.75 volt. Power you can calculate. We are going to get power less than quarter watt. So you can select resistance 270 volt, 270 ohm and quarter watt. Those resistance we will get. In that way, you can design this resistance and this resistance. After that, you can use one buffer also. Open. And also you can design. And you can connect with Hall effect mode sensor. You can connect to one round. After you find out the value of resistance. Because in this case also we are going to reduce in terms of voltage only. The power how much? 1 watt. Resistance how much? 1 divided by 10 milliampere. 100 ohm you will get. Certain value 100 volt. 100 ohm 0.25 watt. These are the setups. We have designed these sensors. 3 sensor, current, their voltage, their supply current, load current. These are supply voltage sensor. This is the DC link voltage sensors. Also, we need to design this isolation circuit. That already we have seen in the voltage case also, DVR case also. So first you can see how much pulse we are getting. What is the amplitude of pulse? Based on that one, based on the converter requirement, you can put. Based on that one, you can decide the here value of that this transistor elements. Based on that one, you can design a transistor circuit. Here, basically we are telling that we have taken the gate pass. That gate pass is going to turn and turn off the this going to get turn and turn off the 15 volt system. What a 15 volt we are given a transistor, that one we are going to make turn and turn off only. And here this optical isolation going to that optical isolation is going to create a pulses on and off only that one. And what a 1 kilo ohm resistance, by that one you can get the required voltage here. Okay. Then point is how we can test isolation circuit and Denver circuit. Those are also there. We have created 2.5 microsecond delay time. Okay. Though that one we need to save the our IGBT during transfer of same leg to IGBT, turn and turn off. This is our experimental data. We have taken 7.5 kilowatt that AC drive, time of 5 HP 440 volts, transistor 5 volt, 5 HP 240 volt, excitation capacitor, and other things. Now the other dynamics, what are dynamics we have taken incidentally also. Current voltage based on the how we want to record the results. You can see here this is main thing. First we have a battery current. When load is increased, the battery is going to decrease here. Decrease in battery charging. Second one, when load is down, high load is down. Battery increase the battery charging. Battery going to increase. This way we can see the phenomena of energy storage element. Okay. Means we should know whatever function I have told, if our load is going to increase or decrease, our wind speed is going to increase or decrease, then what is the effect of this one in battery current? Those we can observe from these points. Also, we should know power balancing also under different speed. Now you can see whatever we want that we have recorded 230 volt some voltage, then load we have created distortion, then we have compensated up to 3.1 3.1% TTLG. That is common thing only. Whatever you can also compensate, you can do simulation work. Second case, we have used one permanent magnet synchronous generator. In previous induction generator, we have changed the generator. And also, since in this case, we don't have a frequency very much. So only we want to compensate the voltage. That is major advantage. Other thing, whatever we have discussed, that 4-wire system is there. For the neutral we have compensated using GJ transformers, and here you have 3 single phase different load. By this converter, we have compensated the reactive power harmonic and balancing those things. Here main advantage we have very less problem due to frequency variation. That is main point. And for that one also maybe you can develop some controller. Here we have used one control based on the mixed or hybrid order generalized integral. Here you can see ABC alpha conversion. Then we have one circuit, and we have find out the value of modify value of alpha beta, then converted to DQ. After that we have a reference current, and that reference current we can use to sense the we have used to generate the required gate signal. We are telling simply only because we cannot tell everything, because you can also not understand. Only we are telling you what are the main thing. Our main thing is we should convert ABC to alpha beta to हेलो मुझे थोड़ी देर बाद फोन करो, आधे घंटे बाद, ठीक है? आधे घंटे बाद फोन करो। हाँ 15 मिनट बाद। हाँ क्या हाँ ठीक है, अपलोड कर देना। हाँ okay. Then after that here you can see here major advantage we have less variation due to frequency. How this circuit is there. This circuit is based on this one mixed or hybrid order generalized integral. So maybe you can say somewhat higher end of the SOGI. After that, this circuit we have implemented, and we have got the somewhat improved response in alpha beta. Then cover the DQ to ABC. Then we have recorded the response. Now main thing is there, you can see these are the comparison. Other thing, okay, this one may you will get less than 5%, and load is whatever load is there, capacity you can observe the power there. But main thing is this one. By purpose control, we can see somewhat settling is somewhat fast compared to previous. Those based on those we can say our system is correct or not. Okay. Also you can compare sense reference signal, SOGI signal and purpose signal. Suppose hybrid whatever order hybrid order general integral are there like that. In that way we can say